Hello all. Let's talk about DNA replication. So, if the origin of replication is here, our friend helicase is going to insert itself here. And I like to draw a helicase kind of like this, because it's going to unzip our DNA this way. Doop, 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 doop. This is a replication bubble. Now, as helicase unzips, on this strand, the 3' to 5' strand, that's going to be our leading strand. And it's a leading strand because it is built way faster than the lagging strand. So I'm going to go through that first. The first thing that happens is that primase attaches. You see that? You can see that. That's primase. And primase attaches a primer, which is a 5 to 10 base stretch of RNA that is compatible with this stretch of DNA. That's the primer. Once the primer is attached, primase dissociates because it has better things to do. Then DNA polymerase 3 attaches. 3. DNA polymerase 3 comes in and it puts DNA this way as it advances and strings them together, like that. And then as it goes, DNA polymerase 1 comes in. Let's use this one. DNA pol 1 comes in after DNA polymerase 3 is already off and running. And DNA polymerase 1 replaces the primer with DNA. Leading strand. Now, when we're talking about the lagging strand, we know it's replication bubble, we have to talk about this 3' 5' business. So, this is what I had wrong in the last video, which is why I'm spending my Monday this way. The DNA polymerase can only add DNA to the 3' end of the growing DNA strand. So if this is 3', that means that this is going to be 5' because they are anti-parallel. Therefore, this is our 5' template end. This is our 3' daughter strand. And DNA polymerase is adding nucleotides onto the 3' end, because that's all it can do. And that's true for RNA primase as well. So RNA primase is going to come here, and let's say it comes here, RNA primase, and it is going to make a primer, and it's going to make that primer 5' to 3', opposite of this, which is that way. And then DNA polymerase 3 is going to come in and grow that as far as it can. But it can't grow it very far. Once it can't go any further, it's going to disappear. or float off, I guess. And then we have our RNA primase coming back further up the line, let's say here, presuming my red continues to work. It's gonna add some primers, then it will dissociate, and DNA polymerase 3 will come here and add stuff this way, again, because this is 5 prime, this is 3 prime, this is 3 prime. So it can add things to a 3 prime end, but it can't add anything to the 5 prime end. This is 5 prime end, this is 5 prime. So we have these weird gaps. That's weird. They have a name. These are Okazaki fragments. Okazaki fragments. These Okazaki fragments can be further elongated by our old friend DNA polymerase 1. After DNA polymerase 3 gets out of the way, DNA polymerase 1 can come in at both of these sites and replace those primers with DNA, but it can't connect these two Okazaki fragments. That job is for an enzyme called ligase. DNA ligase connects DNA, so it ligases DNA. Ligase is just a weird term for stick together thoroughly. And DNA ligase can connect Okazaki fragments. That is how the lagging strand happens. So, again, the leading strand template goes 3 to 5. The leading strand building daughter DNA line is 5 to 3 because DNA is built by adding to the 3 prime end. For the lagging strand, the template is 5 to 3 because the daughter strand is going to essentially be 3 to 5. But you can't build 3 to 5, so you have to build it 5 to 3 in chunks. So it takes longer and it lags. That is DNA replication. For DNA transcription, y'all wanted the initiation and the termination, but you seem to be clear about the middle. That's great. Let's talk about the beginning and the end. For initiation, there's the big important part is the promoter. Which has 2 important aspects, -10 and -35 region. And the -10 and the -35 attract the sigma factor. And the sigma factor attracts the rest of the RNA polymerase, which I'm going to draw like this. Keep in mind that there are 5 more parts to the RNA polymerase complex. But all you need to know is that there's 6 in total, sigma factor and 5 others. Together they make RNA polymerase. And what RNA polymerase does first is it opens up, unwinds and opens up the DNA so that RNA can be attracted, can get to it. And then it allows in RNA that is anti-parallel to the DNA building thing. So that's gonna look like this. And as this progresses this way, the RNA strand that's getting made is going to come out this end. So let's talk about primes, because clearly this is the thing that I'm the worst at, so I'm just going to assume that you're the worst at it. This is the template strand. Template. That means that the resulting RNA is going to be antiparallel to the template. And that means that this is 5 prime, this is 3 prime. This is 3 prime, this is 5 prime. And as we all know, the nucleotides, even RNA nucleotides, get added to the 3 prime end. So for the termination, I'm not going to draw the enzymes. It's the same as the last time. It's just the same. So instead, I'm going to talk about the termination region. The way that transcription terminates is really interesting because it's very physics-y. It has to do with the strength of bonding between the mRNA, the growing mRNA, and the DNA. So, if you imagine it's continuing on, if the thing was over here, it's coming, the thing, RNA polymerase is there. Then it arrives to the termination region, which has a series of in a nice space. There's other stuff in there that isn't C and G, there's A's and T's. Okay. And then there's a series of A's. So, as the RNA polymerase comes on, it's going to build its RNA antiparallel. So, GC, GC, like that. And then we've got our other stuff. But remember, as it continues, this stuff gets kind of loose. So it's going to go out like that. It's still... But look, this and this are also antiparallel to each other. They could interact. And in fact, they will. So as RNA polymerase continues up to this A section, here's our loop. That's the rest of the mRNA. So this is CGCG, this is CGCG, and this is going to be U. And that's an important thing, because there are 2 weird things happening right now. The first is that this loop is creating tension. Because of that tension in the shape, it's going to kind of want to twist off. It's very uncomfortable being all clumped up like this. This is together. This loop is going to kind of want to push like that. So it's going to create tension in this weird way. At the same time, this bond between A and U is relatively weak. It's the weakest of the hydrogen bondings between the nucleotides. So it actually can pull off with that torsion. This is just going to pull off. And that arrow represents the rest of the mRNA, and as that torsion kind of thwinks itself off, the mRNA is going to float along and get translated. So let's talk about translation. I'm just going to give you the anatomy of a ribosome. I've drawn a ribosome with super obvious anatomy. This is the input. This is where the appropriate tRNA will find its home. The appropriate tRNA has an amino acid here that handshakes with whatever codon is here. They are anti-parallel stuff. They're complementary. Bunch of them are going to check. The one that fits and that stays will signal for elongation factor G. Will, using GTP, push this thing, this tRNA, over into the P site. As it does so, it's going to push the amino acid it's stuck to into this amino acid chute kind of situation. And another tRNA will come in here and maybe it will fit. If it fits, it'll get pushed again by elongation factor G. Maybe G for go. Go. This A site, this is the tester site. Too black. For A for amino acid testing. Amino acid testing. This is the P for protein building. As we can see, because when this is correct, our EFG is going to push all of these forward. This guy is just going to scooch on without its amino acid. Its amino acid has been taken off. This is going to scooch like this, and its amino acid is going to come in under here. Whoop! And then it's going to get stuck to the one that was there before. So the protein is getting built in this slot. So it's the protein building slot. E is the exit slot. The tRNA from here is just gonna whoop, leave. That's the mnemonic. There is an EF2, EFTU, which is prokaryotic specific, and it escorts the methionine associated tRNA, which is the start codon matching amino acid. So, and it specifically is associated with the ribosome so that for sure, you'll have an easy, ready to go first amino acid to initiate this process. That is prokaryotic only. EF2 is not in eukaryotes. I think that's all of the things that you wanted to talk about for this. Y'all are wonderful.